I wanted to make sure that in the last two videos, everything that you heard, we have an opportunity to get into our notes. So we're talking about sound here, right? And our first question is, what causes sound? And the answer to what causes sound was vibrating matter. Okay. And then our second question is, what determines the type, and by type here we mean pitch, of sound created? And what we determined then was the material that's vibrating was going to be the first thing. Now, what about that material? That's a little bit more complicated, the question. Yes, it definitely has something to do with density. Yes, it definitely has something to do with the elasticity of the material. It's a much more complicated question than I'm giving it credit for right here. But we're just going to say different materials will make different pitches. And the secondary concern was the length of the vibrating material. All right. And it was very specifically the length of it, not the volume of it, not the width of it, the length. And as a secondary concern, I will admit that there is a correction factor for the width of it as well. But that is very much a secondary factor to the length. But I will acknowledge it, right? And so with that being said, I posed you a question and that I made each of these two wine glasses vibrate, and they made very different sounds. Why? Well, they're actually made out of different types of glasses, different types of glass rather, and you can see that the two things have different lengths of material that would be vibrating, and that's the reason why they made two different sounds. So there you go. So after this, we talked about the anatomy of the sound wave, and then we said sound was a longitudinal wave and a mechanical wave, right? And that longitudinal meant compression, and then we looked at the tuning fork, and that tuning fork tine was vibrating back and forth and created areas of compressed air and areas of partial vacuum. And we have better pictures of this from the video, but I just wanted to kind of just have this so we could label these. These, once again, were called compressions. Remember, they're areas of high pressure, and then the areas in between were called rarefactions. Rarefactions. Okay, and those were areas of low pressure, right? Partial vacuum. And then these were areas of high pressure. And that we figured out that we could represent a sound wave, therefore, as a pressure wave, where the horizontal axis here was 1 atm, which is what the pressure at any location in space would be if there was no sound wave going through it. And if there's a sound wave going through it, let's say it's a nice pure tone. Hopefully you know what that means by now, right? There's some sort of maximum pressure, some sort of minimum pressure. It's not zero. And then the amplitude of this would be how much up from the max, from 1 atm, or how much down from 1 atm that pressure wave goes, right? Because even though I'm representing this as high pressure, low pressure, high pressure, low pressure, it really is a continuum between those two spots, right? And then the wavelength is very easy to see. And this was the pressure wave for what we'd call a pure tone, right? We wrote down on a different document that I will have shared with you the difference between tone and pitch. So I don't want to go into that here, but this would be a pure tone because that sound pressure wave is a pure sine wave, and it looks a little bit different for other sounds, right? So two things could have the same frequency, the same pitch, but a very different tone. All right, so I'm not going to repeat things from the video if I wrote it in the doc. So I'm just sort of adding on to things that weren't written elsewhere. And so the next thing I wanted to talk about was underneath the amplitude. And we were talking about intensity. And I want to define intensity a little bit more formally here. This is actually defined as the power per unit area. Okay? Now notice it's power, which is related to energy. Remember, energy per time is what power is, right? The watt. And the reason why I bring that up is if you've ever bought a speaker or looked on the back of your speakers, you will see that the unit that's always on a speaker is the watt. Because what that speaker is trying to tell you is how much sound energy per second that it is able to give out. So let's say I have my source right here in the center, and let's say it's like a big bass. So it's like that thumping bass, like boom, boom, boom. And you can almost imagine that this source is like pulsating and creates a pressure wave. And that pressure wave, although it looks like a circle here, folks, you got to imagine that that's a sphere because this is spreading out in 3 dimensions. And it is thumping their way at a constant frequency, and there it goes, and it spreads out. So what this is saying intensity-wise is that this speaker is putting out a certain amount of energy per unit area, right? Or sorry, it's putting out a certain amount of energy per unit time. That's what the speaker is doing, power. But as an observer here, if I'm an observer here versus an observer here versus an observer, say, here, those 3 observers experience a very different experience, right? Remember, energy per unit time is what's getting put out here, and then intensity is the power per unit area. So what's happening here is each of these wave fronts, as we talked about, has a certain amount of energy, because if you'll remember how we defined amplitude was energy per unit cycle, right? And if we just think per unit cycle, and that cycle has a time of 1 period, those are pretty much the same sort of definition then. So what's happening here is this person is intercepting a certain portion of the wavefront because of where they are at, say, a distance r1. But if we look at the person who's here, because this wavefront is now much larger, the area that they are taking up of that whole wavefront area is much smaller. And And then here, this person is taking up even less of the total area of the overall sphere, right? And so if this is talking about energy or power per unit area, the further out you go, even though the energy of this wavefront is constant, as an observer, I'm experiencing less of it. And so the way that we like to talk about it is that in terms of intensity. As a wave goes out, its intensity diminishes, even if the energy is staying the same in the wavefront. That's why moving away from a source of sound means it doesn't sound as loud, because what's decreasing here is the intensity. So I want to actually give a formal equation for this now. If it's power per unit area, here we go, power, capital P, per unit area. But what's the area? It's the area not of this circle, but it's the area of the surface area of the sphere that this is on. And the surface area of a sphere is 4 pi r squared. We're going to box that. That's an equation. And this tells us not only why things aren't as loud when we move away, but as we move away, why the loudness decreases fairly rapidly, right? Because of this r squared relationship. It also explains why if you have more powerful speakers, that we can hear them from further away. Now, the next thing that I want to talk about is the decibel scale, right? Sound intensity level, which is a measurement of volume or sound intensity level. I'm not going to get too much into it because it's actually really a complicated mathematical experience here, how we talk about this. So, sound intensity level or volume is measured in something called decibels, right? Or really, I should properly write this decibel with a weird looking B there. It's actually the Greek uppercase letter beta, because that's actually going to be the symbol for it. And deci, hopefully we know, means 10, right? And so that's really important in terms of how this thing is defined. Because technically, volume or sound intensity level, SIL, we won't go into the formal symbol for it, is equal to 10 times, well, there's your deci, the log base 10 deci of the intensity of the sound compared to some sort of constant. And this here is called something called the threshold of hearing. The threshold of hearing is the minimum intensity that the human ear can detect and still register on the audio nerve. And the value for this is 10 to the negative 12th watts per meter squared. It's a very, very, very soft intensity. And so for anyone that's interested, by the way, we're never going to use this equation to calculate anything. I just wanted to show you how complicated it is because it is going to use logs. But the reason why I show it to you is because if we start talking about the decibel scale, just to give you a sense, a 60 decibel sound, that is your average, normal conversation. But then if you start looking at the decibel scale, and I'll show you a chart about that, the decibel scale, a 70 decibel sound, this is actually street traffic. Okay, and then you start getting up to an 80 decibel sound, and things are starting to get a lot louder here. A 90 decibel sound, that one I know off the top of my head, this would be something like a police siren. Okay. Now, the thing about it is, if you have two people having an average conversation at 60 decibels, and let's say we have actually 4 people doing an average conversation of 60 decibels, like if I have 2 60 decibel sounds, 60 decibels plus 60 decibels is not equal to 120 decibels. 120 decibels would actually be something like a really loud concert. And 2 people, or the 4 people having a conversation, is not a loud concert. The logarithmic nature of this scale means that we don't just add them in any sort of normal way. So we're not really going to get into the math of that. If you're interested in the math of that, I will hold an opportunity for people to ask questions about that. But for us, we're really just interested in the fact that intensity dies off pretty quickly as you go away from the source, which then, because that affects the volume level of something. And that's the more specific nature of it. Right. So with that, we should now have notes on everything from the videos that I didn't type into the doc that I will have shared with you. And from here, what we're going to go on to do is talk about the properties of waves, reflection, refraction, diffraction, interference of sound, to prove that those things happen, and maybe do a little math along with that. Now, if you notice, I didn't talk about polarization, and you should know why I'm not talking about the polarization of sound.